Okay, let us discuss this problem. This says there are two different ways of making 2-ethoxyoctane from 2-octanol. So what we are doing is we have 2-octanol. So using 2-octanol, we are preparing 2-ethoxyoctane. And question says there are two ways. First is using Williamson ether synthesis. So this says when pure 2-octanol of a specific rotation minus 8.24 is treated with sodium metal. So you have 2-octanol. So let me write the structure of 2-octanol. So you will having 8 carbon this time. So let me use this structure, bond line diagram. It will be easy for me. 1, 2, 3, 4, 5, 6, 7, 8. Let me count again. 1, 2, 3, 4, 5, 6, 7, 8. Now at position number 2 I have an OH group. So this is 2-octanol. Now question says when minus 2-octanol of a specific rotation minus 8.24 is treated with sodium metal. Now this carbon is optically active. So they will have two isomers. One is R, another is S. So let us take this isomer that have a minus optical rotation. So I am assuming this isomer will have a minus optical rotation. So 1, 2, 3, 4, 5, 6, 7, 8. Let us say hydrogen is in the back for this molecule and OH I have in the front. So this is the molecule we have. Now question says if this molecule is treated with sodium metal first, so I am treating this with sodium metal. Now if it is treated with sodium metal, you know what will be the product. So this is a alcohol react with sodium that liberates hydrogen gas. So you will have O minus Na plus. So simply you have to copy the same thing, and then you have to have right here O minus and hydrogen is in the back, and you will have O minus Na plus. Now this compound further says treated with ethyl iodide, that is CH3CH2I. If this is treated with ethyl iodide, the product is 2-ethoxyoctane. So what will happen? This minus charge, this will eject to nucleophile, this will attack on CH3CH2 and it will release a leaving group I minus. So you will have final product. I think all of you are able to understand this one. This is quite easy. So you will have a hydrogen in the back, and now this O minus will attack to CH2CH3. So you will have O CH2CH3. So let me write OET. So you will have this compound. This is the first route for preparing this ether. Now the B part says this can be also prepared when pure minus 2-octanol is treated with thionyl chloride. So let me call this as step 1. So this is the first way of preparing ether. Now we also have the second way. And now this question says when this same compound, I am taking the same minus isomer. So this is a optically active. So I will be having this isomer, hydrogen in the back side, and OH I have is in the front side. Now question says when this compound is treated with thionyl chloride SOCl2, SOCl2, if you treat this compound with SOCl2, now if you remember, SOCl2 basically OH is removed and 1 Cl is added, and this happens with retention of configuration. So in this, if only SOCl2 is taken, there will be OH that will be lost and Cl will attach here, and that is a retention of configuration. But if you take SOCl2 with base, in that case inversion of configuration will take place. So in this case, you are simply using SOCl2, you will have retention of configuration. So this OH will be simply replaced by Cl. So let me write. So there is a hydrogen and this OH is replaced by Cl. Are you getting? So this goes with retention of configuration. So this goes with retention. Now the second step says, if this compound is further treated with sodium ethoxide, so now we are treating with NaOET. So CH3, CH2, O minus, Na plus. So this compound is treated with sodium ethoxide. Now SN2 reaction will take place. So this will act as a nucleophile, O minus. So this will attack here and this will go up. Now this time this inversion of configuration will take place because SN2 goes with inversion. So in this step, inversion of configuration will take place. So this means configuration on this carbon will be changed. So if I write product, I have to remove Cl and I have to attach OET group, but the configuration should reverse. So let us write the bond line diagram. Here everything will be same, only thing is now OET will be on the back and here you have that is hydrogen that will come in the front. That is the case. Are you getting? So this is the product you have this time. So first here to here you will have inversion. So you see what is happening in the first step is retention. First step, that is alcohol to alkyl halide, ROH to RCl, that goes with retention. Now the second step you have, that is RCl to ROR, that is alkyl halide to ether, that goes with inversion. Are you getting? And finally the product is inverted. Now question says, if the first case the product has the optical rotation, so if I prepare the compound in the first case, this I am getting this product, and this says the optical rotation of this product is minus 15.6 degree. This is given to you. So optical rotation, let us call this compound as A. So optical rotation of A is minus 15.6 degree, and our question asks the product B, that is product from a step path 2, let us call this product as B. So question asks, what is the optical rotation of product B? And I think all of you can tell me what is the product of optical rotation, what is the optical rotation of product B? You can give me the answer, you know basically. Let us try to find what is the relationship. You see this compound H is in the downside and here H is the front side, OET is the front side in this case. Here you have, and here you have OET in the back side. So this means these two compounds are basically enantiomers. So A and B are enantiomer. So if they are enantiomers, optical rotation will be opposite with equal magnitude. So A has an optical rotation of minus 15.6 degree. So this suggests me B should have an optical rotation of plus 15.6 degree because this is a enantiomer. So I think all of you are able to understand this one. This is a quite good problem. So if you use thionyl chloride simply, it goes with retention of configuration. But if you use thionyl chloride in the presence of base, in that case you will have inversion of configuration. That is one important point you should to remember. So what I am saying, I want to summarize this one. So let us say you have an alcohol. So let us say simple example. You have a hydrogen here and OH here. Now if you use simply SOCl2, what you will have, you remove this OH and put a Cl group. And here you have to remove and just put a Cl group. So this goes with retention. Now if you have the same compound, H here, OH here. Now if you treat with SOCl2, but in the presence of some base, let us say generally pyridine is used as a base in these reactions. So pyridine, and that is a base. If you use base, what will happen in this time? It will not go with retention, it will go with inversion. So Cl will attach in the bottom side and hydrogen will come in the front side. So this is the inversion of configuration. So this is an important point you can remember. If SOCl2 is simply used, this will give you retention. If SOCl2 in the base, in the presence of base it is used, this will give you inversion. This is sometimes also called SNI reaction. So this reaction is SNI. And what is the meaning of SNI is inter-substitution nucleophilic intramolecular. So this is intramolecular nucleophilic substitution. Sometime we will discuss in the class what is the mechanism for this reaction. This is intramolecular, of course, intramolecular. So let me write the mechanism here itself. So what happens in this case? So here I have hydrogen and here I have OH. Now this lone pair, I have SOCl2. So this lone pair attacks here, this opens up and then returns back and Cl goes. So let me write H O S O minus, are you getting? And there is a hydrogen, there is a plus charge on this oxygen, and there is a Cl and there is one more Cl. Now in the next step, this attacks and the CCl attacks on the same time. So you see, this bond is never broken completely. This bond is breaking and this opens up. So you see what is happening. The same molecule is acting as a leaving group. This molecule is acting as a leaving group. And the same molecule, one nucleophile is attacking. So you see, nucleophile as well as a leaving group is coming from the same molecule. And that comes from the same side. And that's why this is a intramolecular nucleophilic substitution. So this does not permit to have inversion, because this molecule will be only on the one side of the phase. This can attack only from the same side. This is hydrogen. The hydrogen remains in the back of the plane. So attack happens from the same side. Attack happens in this case from same side. Are you getting? And that's why this is called intra. So this gives you intramolecular nucleophilic substitution. Intramolecular nucleophilic substitution. That is SNI. Intramolecular nucleophilic substitution. Okay, if you have copied this one, we can go for the next problem. This is quite interesting. This is a good mechanism. You have to remember, sometimes question is asked related to the mechanism. In that case, you have to see if it is used in the presence of base. In that case, inversion of configuration will take place. If it is used without base, retention of configuration will take place. And when it happens with retention, the mechanism is very simple, and that is SNI mechanism. We'll discuss the next problem.